Hi everyone. We looked at the kinetic energy, the gravitational potential energy, and the spring potential energy related, and I said in the last video that the spring potential energy is strongly related to the spring force. We haven't seen what that is yet, because I wanted to, but when I modified my notes for this semester, I forgot that I wanted to, and anyway. The spring force is this. Again, I'll go to sketching the three possibilities of a spring at equilibrium, stretched or compressed, and we'll explore what's going on. We have here the three possible situations. Either the spring mass system is at equilibrium, or it is stretched, or it is compressed. No other choice. We established that the equilibrium position, x equilibrium, is where we take x is equal to 0. Contrary to the gravitational potential energy, where you could choose where h is equal to 0, here you don't have a choice. Equilibrium, x is equal to 0, no displacement, no spring potential energy. You cannot choose otherwise. This is set in stone. The spring force, think of what a spring does. You can think of a slinky if you wish. You can think of the shock absorbers on a car, the bumpers on a car. Not really the bumpers. Bumpers, no, ignore the bumpers. You can think of a spring that allows a kitchen door to swing open and close in both directions, but slowly closes. Right? All of those are examples of springs. What you'll notice if you take a spring is that if you stretch it, spring wants to go back to equilibrium. So, for example, in this case, the displacement points towards the right. The spring doesn't like that. It wants to come back to equilibrium. It will force the mass to come back to equilibrium. And so on the mass here, there is a force, the force of the spring, that points to the left. That force obviously is proportional to the displacement. The greater the displacement, the more the spring is stretched, the more it wants to come back to equilibrium. All of this is exactly the same when we compress the spring. The displacement here, when you compress the spring, points to the left. It is negative. Well, the spring doesn't like that. It doesn't want to be tight and compressed. It wants to expand and take its proper place. So it will do just that. It will want to create, and it will create, a force of the spring on the mass that points to the right here. And if we let go of the mass, in either case, they will go back to equilibrium. Obviously, at that point, and if you'll have seen this at one point or other in your life, you'll see that the masses just start to oscillate back and forth. That's because when you start here, for example, you have a lot of spring potential energy. At equilibrium, you don't have spring potential energy anymore. But energy is never lost, nor it is never gained. It is always conserved. It's one of the basic principles of energy. So where does it go? Well, it goes into kinetic energy. But here, that kinetic energy means that the mass is in motion. So it keeps moving up until all of the kinetic energy has been transformed into potential energy. And then it stops. And then it starts going in the other direction up until the spring is stretched. And then it comes back and forth and back and forth, and you have an oscillation. This is the starting point of the third course of physics, Waves, Optics, Modern Physics. It starts with oscillations like this, so you will see that again. For our purposes, all that we care is what the energies are. Because it'll be useful, we can draw a couple of conclusions from this. We see that the spring force, as a vector, is always, let's call it anti-parallel. I don't know if that's the symbol for it. I'm going to use this symbol. It's always anti-parallel to the displacement. The angle between those two is always 180 degrees. If, as soon as you have some stretch of the spring, the force wants to bring it back. If you have some compression, the force wants to bring it back. So you always have this. The other thing is that the magnitude of the spring force, this is done by experiment, is proportional to the magnitude of the displacement. So considering those two things, I can't remember what his first name is, Hooke, established what the Hooke law is. The force of the spring is negative some constant times the displacement. And it turns out that this constant here, K for constant, I don't know what it was, it turns out with the experiment that it is the spring constant of the spring. So, it keeps its name. In magnitude, it would be written like this. But you must always remember that it goes against the direction of the displacement. It is what's called a restoring force. It wants to restore the equilibrium. It wants to bring balance to the force.